Yeah. So in the last section, I was too slow, and there's still a little bit of code left. But I think what is more useful, because that is only a more in-depth and more complex workflow that reuses the same basic principles, I would give everyone the opportunity to, at the end of this section, once we are at the end of the theoretical input, so to say, decide on what type of content they want to see, whether I should present the more complex work flow with DataLad basics, and you can read up on that also in the code along section in the handbook if you are curious to find out what it does, whether we want to do something with reproducible paper or with containerized pipelines. But first, I'll start with some theoretical input on reproducible research in general. And something that is nicely demonstrated in this figure here is that a published paper is only the last step of a pipeline of decisions that have been made that have modified the data or the code that generated the results, or anything that that had an influence on the final result that is reported in the paper. And when you share a paper with someone else, then the findings that this paper reports are, if you want to be really, I don't know, cruel, so to say, they are just a statement that one can decide to trust or not trust. If no one has the ability to take a transparent look into the pipeline that generated the paper, then it is questionable whether the results that are reported in the paper can reproduce on another system or actually hold. And it's also much harder to build up on the results that are reported in the paper. And there's this famous paraphrased quote of Jean-Claire Baud, who was a pioneer in reproducible research that I very much like. And he says, an article about computational science in a scientific publication is not the scholarship itself. It is merely advertising of the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions which generated the figures. And he did say that in the 90s. So that's already quite a while ago. But I think if you've been involved in science, in reproducing others' results, in taking up a project that another person has worked on, then you probably share this general sentiment that you need the complete set of instructions which describe how a particular result came to be in order to reproduce it. Else, it's really, really hard. So, from my personal experience, for example, back when I think I did my master's thesis, we were using eye tracking data and we were analyzing it, and we were searching for an algorithm that was capable of analyzing these eye tracking data, and we found many papers that reported phenomenal results of their algorithms, but it was just bragging. It was, here's an awesome finding, our algorithm really performs well, but the algorithm was behind closed doors. It's not only that it most often was written in programming languages that were closed source software tools where we didn't actually necessarily had the means to execute the code, but the code actually wasn't shared. So they had this algorithm that could do something that we also wanted to do to base further research on, and we weren't able to get there. And that was a motivation for us to then actually implement our own algorithm, just out of necessity, because it left us no other choice. And this is how I want to kind of motivate the section on reproducible science, and to give you some ideas on how to be better than that, and to illustrate some workflows from my own from my own workflows on how I do this. I actually need to get rid of these headphones. That's a weird echo that I'm getting. Now I can talk more freely. Sorry. Okay, so first I want to give a quick reminder of the definitions that have been already a part of the concept section that I PowerPoint karaoke'd when Lennart was briefly offline. So there are these 4 important concepts: reproducibility, replicability, robustness, and generalization. And all of them are part of the scientific process and important to distinguish from one another. So when we talk about reproducibility in this context here, then we mean that we get identical results when we have the same analysis run on the same data. So basically what the DataLad run record did in the last section. When we talk about replicability, then we reuse the code, the analysis that we have run, but we run it on different data. And if that produces similar results, then we talk of then we call a result replicable. And a result is robust when it's the same data, but a different analysis, tweaked parameters, a different implementation of the same algorithm, and so forth. And a finding is generalizable if it holds, or the hypothesis or theory holds, if we have different data on a different analysis. And the basic section has probably shown you that the reproducibility aspect, that's quite easily actually to see or to ensure with the basic DataLad run or containers run command. But I also want to highlight how all of these other 3 concepts can be at least eased with some of the tools and workflows that we talk about in this workshop. And the first thing that I want to do is I want to walk through a checklist that I personally find really helpful. It comes from a book that Konrad Hinsen published this year on computational reproducibility. And that's a really good book that I definitely recommend reading. But he has digested or distilled his advice for general computational reproducibility into a checklist, and that's completely independent of DataLad or any of the tools that we talk about. It's just a general checklist of things. So even if you're not interested in using DataLad, then that's a checklist that holds true regardless of whether you're actually using DataLad or not. So one thing that Lennart already has mentioned multiple times is that you should use code and scripts. So workflows that are based on point-and-click interfaces, for example, Excel, they are not reproducible. If you enshrine computations and data manipulations in code, it's much easier to associate a change with the code that produced it. Then document. Use comments, computational notebooks, README files to explain how your code works and to define the expected parameters and the computation environment required. That's both for you and your future self and for your collaborators and the people that read your research. Then record. Make a note of key parameters, for example, seed values that are used to start a random number generator. You should test, and that's a concept that comes from software engineering, and it's definitely not easy to implement. But if this is the first time that you have heard of unit testing, then that would be a concept that I would really recommend you to Google. The Turing Way, for example, has a very nice introduction to that, and that's something that is extremely powerful and helpful to ensure that you can trust the code that you have written. So testing involves creating a suite of test functions in whatever programming language you use or scripting language. And then you can use positive or negative control data sets to ensure you get the expected results, run tests throughout the development of an analysis pipeline to see whether there are any unexpected things that it does throughout the development. And then you can much easier identify bugs in your code that make your code faulty or non-reproducible and so forth.
Yeah. I just had a comment. I mean, since we agreed that we wanted to make this a bit more
yes, right,
lively, I wanted to, I just had a thought about testing. So at least in my impression, at least in cognitive neuroscience, testing is like explicit testing is rarely done, or somewhat more implicitly. But I often also notice just in my own work that often I just do like simple checks, but I don't kind of write them up as extra scripts. I don't know if this is helpful for others, but when I notice this, for example, I would have a data frame in my workspace of whatever R, Python, and I would then calculate the number of rows to check if they make sense and stuff like that. And but I never really paid attention to writing them up explicitly in a test that I could run on data. And I don't know if maybe other people can also say something about this, but from my impression, that is often the case, that we do this somewhat implicitly, or we do it in some way, but not in this more formal way, that it can be really used on larger scale and that these tests can accompany the project throughout its lifetime.
But it's also a step-by-step process, right? So of course, when you start writing unit tests for scripts, then it's likely that you won't end up with the perfect test suite, perfect test coverage, and so forth. But it has saved me so many times already when I just had in Python assert statement in just my workflow script that asserted whether general truths held, like the amount of observations was correct, the right amount of data files was read in. So that already is a step towards ensuring that your code works.
Yeah.
Okay, then what Hinsen also includes in his checklist is guidance. And he says, for example, creating a master script, for example, a shell script called run_sh that performs all of the necessary steps in the correct order with the required data downloads, with the required parameterization, execution of the workflows, and so forth. And that's definitely helpful, because if you have a very large project with multiple code files, and it's not clear in which order the code files have to be executed, especially if they produce output that other scripts rely on, then having such a guidance script can be incredibly helpful for you when you revisit the project later and for others. And later, we're talking also a little bit about makefiles and how they can help with this. Then another thing that may not be obvious to do in order to ensure reproducibility is Archival. So while Lennart and I stress the importance and the niceties of repository hosting services such as GitHub and GitLab, those things are probably not very likely to survive until the eternity, because they are corporate solutions. A GitLab instance that's run by the MPI is likely to survive, but if the IT runs out of financing or something, then that GitLab instance will die. But there are archival solutions, for example, Zenodo, Figshare, or Software Heritage, where government institutions stand behind and where it is ensured that anything that you archive there is preserved for, let's say, 50 years, for example. And all of these solutions are in most cases free and also provide quite ample storage. So if you're a European researcher, then you can use Zenodo to archive up to 50 gigabytes, and you can ask them for an extension just as an addition, as a preserved, archived state of your project. And if that's preserved, then it is ensured that others can at least access it in 10 years, in 20 years. And that is a prerequisite for reproducing whatever you have done in this project. The next thing that Hinsen recommends is tracking. And he says to use version control tools such as Git to record your project history, note which version you used to create your results. And I would definitely agree to that, and would probably say that there is an easy way to do this that does not even require Git knowledge with DataLad. Then he talks about packaging, which is creating ready-to-use computational environments using containerization tools. For example, Docker Singularity, web services such as CodeOcean, Gigantum, and Binder. And Binder is, for example, also a really nice service that you can use to just have a computational environment spin up with a GitHub repository. So if you've never heard of that, we won't talk about it, but you can just Google it. It's quite nice. And also virtual environment packages, managers such as Conda. And later in this session, we'll talk about software containers. And you've already seen how you can have a software container added to a dataset. And I will shed a little bit of insight into how my workflow for creating software containers looks like typically. Now, the last points on the checklist are automation. And Lennart will show concrete examples of that from his work at the end of the session. And Hinsen recommends to use continuous integration services, if, for example, Travis CI, that can be used to automatically test your code. And those are services that can also be very easily and nicely integrated to GitHub or GitLab repositories. And you'll see a concrete example of that when Lennart showcases some of his work. And then Hinsen recommends to avoid niche or hard to install third-party code libraries that can complicate reuse, and to verify in the form of checking code's portability by running it in a range of computing environments. And those are obviously also very, very true statements. And I wanted to highlight in this section that DataLad is one tool out of a great range of free and open source software tools that can make reproducible research easier to do. And I wanted to take a more detailed look into some of the ways in which DataLad can help with this. In particular, I first want to just briefly highlight some miscellaneous facts about DataLad functions. Then I wanted to revisit these Yoda principles for reproducible analysis, then showcase how DataLad can be used as a component in reproducible papers, and give you an idea or several ideas of how to produce a reproducible paper. And then I want to talk a little bit more about the DataLad containers extension to add in new software containers, and about container solutions in general. Okay, so first, for a little bit of miscellaneous DataLad facts that I wasn't able to incorporate into workflows, or that I just wanted to highlight again to just harden or to just give you another reminder of that. So or just general for your interest facts that I found useful in my everyday work. So Hinsen says to use code and script, and that workflows based on point-and-click interfaces are not reproducible, and that computations and data manipulation should be enshrined in code. And first of all, yes, absolutely, very, very much so. But this is something that some people may not be used to work with. So some people may just open up a MATLAB session and then compute their results and save them into the dataset, or in an interactive IPython session, or a JASP or SPSS session, or whatever. And that doesn't leave a trace. Neither is there anything enshrined in code if it's done in an interactive session, nor is the date and time and author of a figure or a result saved in any form. And if that should be a part of your workflow that you really don't want to let go of, so I would certainly always recommend to put everything that you do, write it in code, try to keep some sort of record in it. But at the very least, one thing that you could do to at least attach provenance about an author and the time of a change is to do whatever you're doing interactively in a DataLad run session. So when you do DataLad run IPython or DataLad run MATLAB or RStudio, then whatever program you specify will open up in your typical interactive session. And once you close it, all of the results that you have saved in the wake of this interactive session into your DataLad will at least be saved and associated with a bit of provenance. It's crappy provenance, but it's something. And that is already one way of keeping a data set a little bit clutter-free. So there's not this, I'm going to experiment a bit, and then I'm creating here 5 figures there, and then the next day another 2 figures, and then if I take another look a week afterwards into my data set, and then there are all of these untracked files. With that kind of workflow, they are at least saved and associated with the date, and that's better than nothing. But still, I don't want to I can't stress this enough. A code script that is actually documenting what you do is obviously the best choice, or the better choice than that. Okay, now then there are obviously these rules for documentation and records. And I just want to highlight here that it's great to have human readable workflows documented in a README file or in a changelog, or any of those files that you add to a project that are meant for human consumption, and where someone who gets to see your dataset without knowing you or without knowing anything of your project knows immediately where to look for information for. It's really, really important to have those files. But I also want to stress that commit messages and run records can do the very same thing and are a really useful basis and extension to the documentation for humans. So if you make sure that you have very well-maintained dataset history, version history, if you're using it, then such digital documentation or records or provenance that sticks to the dataset or the Git repository that you compute your results in is really, 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 really valuable, and especially great because it's machine readable. And then there's also what I've shown you in the basis workflow, the Yoda procedure that automatically populated a repository with README files, for example. That's one way of nudging people into actually populating and using those READMEs. And if you are a PI and you would be interested in, let's say, supplying your students with a setup for such a data set, then you can write your own procedure that creates the types of files that you want your students to populate, to just create the infrastructure then that people can build up on. And that's very, very helpful. And that's, for example, also something that we in our institute are soon to be implementing for new projects, just to get people started.
Adina?
Yeah.
Maybe just another 2 cents from my side. So just to give an example from my own experience, this kind of documenting, I've also found it useful to really get into this mindset, to really try to document everything that is kind of important to know about the data set actually in the data set. Like, for example, in these README files, I mean, there are ways, again, with additional software, but not necessarily, to write extra documentation that contains a bunch of text files that can then also be rendered into some website-like documentation of the project and so on. And I found this very helpful because then everything is in one place. And again, I mean, we saw at the beginning, right? A lot of people actually report that they have code and data and nodes scattered all over different hard drives and computers and so on. And I mean, everyone has their own style of taking notes and working, and I think that's also totally fine. And you can take notes in whatever, on a sheet of paper on your desk, or in some extra note-keeping app, or whatever you use, right? Just to share my personal experience, I found it really useful to just make this all in one place, in one ideally version-controlled data set, kind of right next to the data, right next to the code, where everything is really tightly packed together, basically.
Yeah, and that gives others the chance to also get an idea of what you have done. So I always like this supervisor-supervisee example. If a a student, a graduate student, a master student has a digital lab notebook in the form of a well-maintained Git history, then a supervisor has really easy means to find out what has been done, to check code, to really go into the project. And that's making life significantly easier, in my opinion.
Yeah, and maybe just to quickly mention another aspect. So maybe some of you actually know issues. So for example, GitHub or GitLab, usually with each project, there's a dedicated section on GitHub and GitLab where you can open up issues about the code, where you can basically write down bug problems, whatever, ideas, future requests. And I mean, software developers really use this to communicate about all their changes. And Adina also mentioned it before. And that's also actually nice because right next to code or on the platform that you're using anyways, like for example, GitHub or GitLab, you can have these issues. You can link people that maybe you should comment on that or that you ask for help, for example. And then you can have discussions about certain features or problems. And then actually you can also relate changes in your data set or in your code to these issue discussions. And then again, you have a very tight link between really just discussing problems in any way you want, and then actually relating it to concrete changes in your code or data. That's also really helpful in my opinion.
Yeah. Okay, then there is this notion of tests. And also there, yes, definitely, it's not an easy thing to do. It's not a straightforward skill to have, and it's certainly not taught in most programs. I'm a clinical psychologist. I didn't know shit about unit tests ever. Never heard of it in any of my lectures. But that's why we try to mention these things, just for you to have an idea of, yeah, that's a concept that exists that may be helpful. There's also a chapter in the Turing Way that is an introduction to unit tests and how to do it, and that's a really good thing that I would recommend you using. But I also want to stress that DataLad provides, because of the content identity hashing that is done to text files, one way of actually ensuring that if you run something again, if you tweak an analysis pipeline and then recompute it, that this is a way, or version control in general, to just have a computer, a machine, tell you about something that has changed outside of a unit testing framework in addition. And the software tools that you're using, be that GitAnix, Git, DataLad, they will be able to tell you this. And that's just something to keep in mind, that this can also be a helpful addition. Then the master script, or the guide that takes someone through your complex analysis in a single entry point. And definitely, yes, and I'm going to show you a concrete example in the reproducible paper section on that. And here I just want to stress that a well-made run record that works on different operating systems, that has software environments attached at best, can do this too, or at least help. So that's a useful addition to have for sharing a dataset, because it provides this easy to use access point for people that are completely unfamiliar with your project. And if you provide them with a DataLad rerun command that they can execute, then that's already a significant improvement to just sharing a dataset without any notion of what to do with it whatsoever. And then there are makefiles, and I think some people that are attending this workshop already know a lot about makefiles, but they are also great because they are basically a recipe that you can use in order to link or manage workflows in the appropriate order and execution time. And I'm going to have a glimpse into one later. Okay, then the point about archiving, this is where I wanted to note that if you have any dataset with whatever contents, there is one DataLad command that can export it straight as a zip archive to Figshare. So Figshare is a service that does archiving. It allows you to attach meaningful metadata to it, and it generates a DOI that you can use to cite whatever it is that you put there. So I, for example, frequently put scientific posters up there so that I have a preserved record that I can point people to or create a QR code and so forth. So there is the DataLad command export to Figshare, that if you have a Figshare account and a token that you provide to DataLad, takes your dataset contents and exports them to your Figshare archive. And if I have exported Figshare, I'm here, it asks me, would you like to create a new article, or would you like to use an existing one? I say, I want to have a new article. Then it asks me, what name do I want to give this article? And then it performs the upload and puts it to Figshare. And then on Figshare, I have this new collection, and I can use the web interface of Figshare to attach the metadata for. I can finalize the archival of that record and get a DOI that I can then point others to. Note that this is not a data set, so you can't clone that, but it's, however, Figshare reports the data given to it as a zip archive in this case. So you lose the version control and the revision history, but you have performed an archival of whatever it was that in this state of the dataset has been done in the dataset. All right. Okay, so about packaging, we have already shown you that the DataLad container extension can help to do this. And later in this session, we'll also highlight a couple of the tools that are used to package up software, Docker and Singularity, and some helper tools to get you started. And yes, unless you have something to add, I think I will go again to the Yoda principles. Yeah, okay, cool. So just to stress this, when I, in the basics section, briefly talked about these principles for intuitively and reproducible data analysis, I mentioned a couple of things that may be unfamiliar or not as you're used to. For example, the separation of input data and output of results, and this modular and nested structure. And that is something that may or may not be something that you've already done. And I just wanted to stress that a data set can have absolutely any structure. You can populate it however you want. You can nest it however deep you want. You can also use as few or as many features of DataLad as you wish to. You don't need to use run records. You can also only use it to dump in data and publish it. But if you're doing a data analysis, then the Yoda principles, they are a beneficial set of features. And I want to just use this point at the workshop to take another tour through these principles and try to explain why they are useful, because some of these rules may be counterintuitive for you. So the one thing that maybe little bit weird is this modularity, and that's summarized in this principle of one thing and one thing being one data set. So in principle, the principle boils down to bundling all components that are standalone units into a standalone data set, and then taking all of these individual components and bundling them up into one super data set that combines them as individually version-controlled units with their own revision history. And whenever you ask yourself, or whenever something that you create, be that data or be that, I don't know, a software toolbox, whenever something can be of more use than just one time, then it's beneficial to put it in its own data set and install it as a sub-data set. So with this, you can keep a clean and modular structure that helps you to have a very solid border in the form of dataset boundaries to, for example, separate code and output and data or execution environments, so to say. But even though you have this intuitive structure that separates those components, you can still operate across them without being aware of these borders, because DataLad blurs the borders quite well between dataset structures. And then the reason for why this particular notion of installing input data and then never touching it again, not putting results data right next to it, which is something that a lot of people, I think, do. That is, I think, exemplified in this very short example quite nicely. So let's say you have an original dataset that looks like this. It's just named dataset. It has a sample 1 and a sample 2, and each sample has a .dat file. If you then add output data to the input data and you place it in the exact same location as the input data, then even if you would use domain standards such as bits, for example, it requires your brain or an expert or domain knowledge in order to dissociate input from output data. It's not immediately clear from the structure of those directory trees alone. And it is never a good thing, or if you can prevent it, then produce your projects in a way that your brain is not a requirement to make them understandable or working. So if you would instead take the raw data set, but have it as a standalone component here as an input section, and then have the derivatives of those inputs somewhere else, then this structure makes it possible for anyone, regardless of whether they are in the same field as I am, have knowledge of the same naming standards I use, file types, to much more quickly dissociate those two, the input and the output files, from one another. And here are a couple of rules of when it might be useful to modularize, because that in some cases may not be super straightforward. So one guideline on when to modularize is when the target audience for a dataset is different. So it's, for example, public versus private data, or if it's domain specific versus domain general data. Another set of guidance is if the pace of evolution is different. So you may want to archive the factual raw data as one data set, and then the different choices of preprocessing flavors that you can apply as individual data sets that use that as a sub-data set. And the same for a completed acquisition, which should be its standalone data set versus an ongoing study, which you can maybe collect into the same data set or bundle up once it's done from individual data sets. So let's say if you have a fMRI analysis and you acquire data over the course of 2 years, then you can add all of the DICOMs, which are thousands of files, into individual data sets, for example, to then, once the acquisition is done, bundle them all up into a general data set for your acquisition. Another important point on when to modularize that is especially relevant for people that do neuroimaging on big data, so that's something that our institute does frequently, is when there are size constraints that would, or when the sizes of a data set get so large that they would impact I/O performance or any logistics on the file system that it's on. So when you've ever had the chance to try to break Git, then the one way of doing it is if you add too large files to it. That is, that problem is circumvented with Git Annex. But another way to break it is if you place too many files into a Git repository. So with 1 million files, you can be quite certain that Git has plenty of problems and does funky things to your computer. Then you wouldn't want to go there, even if it's just an empty text file that you put into Git. But that's where Git stops working correctly. And in order to nevertheless version control datasets that have way more than 1 million files. So for example, the Human Connectome project dataset that we're version controlling with more than 15 million files. One way to do it is to just split it up in datasets that are then linked together in sub-dataset hierarchies, which is a way of keeping everything operational and importantly operational in a monorepo-like fashion due to recursive operations, but without being affected by those limitations that Git has. Then something that we have been finding out or working around with, let's say, the UK Biobank dataset, which is a dataset that will at completion have 100,000 participants. Some file systems don't have space for that many subdirectories in a single directory. Some file systems are capped at 64K. Other file systems struggle with large amounts of inodes. So just the amount of files on the file system can be too much. And we have written a complete chapter in the DataLad handbook on concrete tips on how to handle such like scaling up issues with DataLad that can make it possible to do reproducible science, even though you do it on 300 gigabytes or 3 terabytes or 30 terabytes of data and millions of files. And then one important aspect that especially those people that deal with data that falls under GDPR, so privacy law, should keep in mind is that there's an important distinction between personal and anonymized data. So while you, let's say, Lennart, who is acquiring an fMRI study, can place the anonymized fMRI data into a dataset that he can share later with others. He doesn't want to do this with the DICOM files, for example, because those are unanonymized files that, for example, contain the faces of his participants. And if he separates those two data entities in separate files and separate datasets, then he can make sure that he doesn't share removes access from the DICOM files to outsiders, whereas he can freely share the processed, anonymized fMRI data.
Adina? Maybe again 2 comments. So I just wanted to comment on the aspect of dataset nesting, because I still remember, like, having learned about DataLad rather recently, that especially this nesting aspect can be confusing in the beginning, because at least to me it seemed like a different way of organizing files and directories on my computer than I was used before. So before I used DataLad, I would usually have like maybe one project folder, and then for example, neuroimaging project, I would have a folder for bits data. Then next to it, I would have a folder for fMRI prep data, and then yet next to it, a folder for some analysis that then uses the fMRI prep data. So you had this illustration before where you actually nested, with DataLad, you actually nested all these data sets into each other, which then basically means you have your project folder, well, maybe not even the project folder, maybe you do have a project folder as some sort of super data set that combines all your possible data sets. But let's say you collected, like Adina said, the DICOM data, then this will be one data set, and you will nest this. So on your computer, this will be a subdirectory of your bits data set. Whereas maybe if you used a similar organization like I did before, then before it was kind of next to it, but now it will be as a subdirectory of this bits data set. And then eventually the bits data set will be a subdirectory of the fMRI prep data set. And this will be a subdirectory of the analysis data set, exactly like it's illustrated here. So I just wanted to highlight this point again, because I found it admittedly a bit confusing in the beginning, this type of nesting. But then and then also this other aspect that you mentioned, that DataLad blurs the borders a bit between these directories. I think that's definitely a very cool and aspect of DataLad, but also in the beginning, I thought it was a bit confusing, because then I would have this bits folder, and then I was reminded, aha, that's actually a sub data set, and not just, again, like files that I can just access. Like Adina said, it's usually not a good idea to then start changing the input data just like that, but rather keep the input as it is and only kind of update this subdata set in an extra step to then update all upstream analyses. So it requires a bit of rethinking, and I guess that's the only point I wanted to make here. But also, I think Adina will now talk about something, how DataLad makes this linking of different data sets very explicit and in this way actually very transparent.
Yeah, and also Ben and Michael added some important points to what you have just said. So one thing that Benjamin noted is that one way of conceptualizing these super data set, sub-data set relationships is to think about it in terms of dependencies, like with a software package where you can conceptualize, let's say, input data as a dependency of the output data that belongs to a super data set, which is one way, I think, of having a mental concept that even with something that may be perceived as a counterintuitive structure makes sense. And then also Michael noted, and that's based on what we are doing in our institute, is that both representations are obviously equally useful and in use depending on what you actually want to achieve. So this nested this next to each other structure, this can, for example, as Michael points out, is this can be incredibly helpful if you just want to archive a couple of data sets. So all of the studies that have been taken place during the last 2 years, let's say, and then having them all right next to each other simplifies access to them immediately.
And sorry, sorry, you go ahead.
No, and I'm just reading out comments and trying to attach more content to them. So Michael says, for processing, those nested views are more useful. And I like this graphic here a lot because it has this pipelining and workflow and evolution aspect where someone that reads the paper, if it's shared in a way that allows it, can trace back all of the steps and can reuse the components that they may need to base their own analysis on them. And when we start processing our input data, then the input data, that's one thing that we distribute globally, and then everyone clones that into their project data sets, processes it however they want, and then that continues.
I just wanted to say, actually, I just wanted to write Michael about his comment, and so exactly the way he proposed it, I try to set it up now for my current project, where I have a kind of a super data set that is really just like a data set containing other data sets, which are all these different subfolders like bits data, raw, DICOM input data, and they all exist kind of next to each other. But then all of these individual subdata sets then contains the other needed data set as a so-called dependency, like Ben also commented. So each data set then has its required data set input dependency, but eventually in this one super data set, project data set, they are all kind of next to each other, really serving more archiving purposes, as Michael said.
Yeah, and I think once you showcase that, it also becomes much more obvious for people that maybe have no idea what we're discussing about currently. So everyone needs to be patient and wait for the real life example.
I think what I just wanted to transport is that at the beginning, this can be a bit confusing. For example, the bits data set, in my case, this is a kind of dependency or subdata set for many other analyses, because in the bits data set, I store information like, let's say, demographic data of the participant, or behavioral data that kind of participants did the behavioral task while they were in the scanner. So this is the behavioral data as part of the bits data set. So actually in the analysis subdata, in the analysis data set, if I just want to run a simple behavioral analysis of the behavioral data, the bits data set needs to be an input to this analysis data set. So then it will be included there. But then also bits is included in the fMRI prep data set, and bits might be included somewhere else. So everywhere you can find this bits folder basically, but it's always the same bits data set that in this way only exists once. But then for a user that is more used to, there's just one folder that contains this data in this kind of next to each other fashion, it can appear confusing that this bits folder appears more and more often in all these different subdirectories. That's all I just wanted to highlight.
Yeah, thank you. Okay, now the second principle, that's record where you got it from and where it is now. And you've all seen examples of that already and have gotten a glimpse into how it works. And that individual subdata sets can be linked to each other. And in this dependency-like forms that subdata sets are, we can record where a subdata set came from and in which version it is linked. We can record where data comes from, for example, the PNG that I downloaded with DataLad download URL. And that may not be a PNG, that may be a code script that comes from a GitHub gist, or that is shared via a collaborator or at a blog post and so forth. Recording data origin is one way in addition to fulfill this principle. Then it is important, and I've tried to showcase that already in this very short script that I've shown you, to keep a dataset self-contained with relative paths. And that is also something that is true regardless of whether you use DataLad or not. Because if you use relative paths in your script, then you have created a portable script that you can move around different infrastructure. If you use relative paths that do not encode the file system into your script, then you can have it run on a computer, on a laptop, on a compute cluster, or on a supercomputer, and so forth. And if you bundle it up in a DataLad dataset, then it's actually this very transportable unit that you can just clone to different places. And then obviously share and publish datasets to collaborate. That is very, very useful and part of the next session. Here's again this information on how datasets are linked, just to give you another reminder of how it works. So there is a dataset, it comes from somewhere else, for example, from GitHub, and it is linked into the super dataset. And what the super dataset stores is a path to where it is, a URL where it can be retrieved from later, and a subproject commit that identifies the precise version. And if that's an input dataset with data, you can really identify in a digital entity which data you used in order to compute a result. And here's such an example, modular data structure from a exemplary and extraordinarily well-maintained neuroimaging example, where you have an analysis that contains code in third-party libraries, maybe linked as additional subdata sets. And the inputs are then this hierarchy of subdata sets that can be traced back to the original bits dataset that, for example, came from OpenNeuro and that you based all of your analysis on. And then the last principle of recording what you did do to it and with what is related to the digital provenance of the dataset contents that you create. And there are DataLad run and DataLad containers run commands that can do this, but already commit messages go a long way. So you have a lot of means in a DataLad dataset to attach digital provenance to your files. Okay. Unless there are questions, so if you have questions, then please voice them in the chat or come and discuss with us. I want to showcase how one way works of going beyond a PDF and sharing code data and software in the form of what many people would call a reproducible paper or a dynamically generated document. And I wanted to do this as a live coding session, so where I explore with you how a actually published reproducible paper works. And I will just do this terminal that I like more. I'm going to go into a temporary location. There's a question, though. I'm interested how DataLad actually resolves the problem of the base path to which the files are relative. Is that a DataLad function? Just curious. I think Michael takes care of that question in the chat already. Okay. You can also just speak up if that's faster, Michael, if you want to, of course. Okay, I think the question is somewhat answered in the chat. I will just start to demonstrate how we have written a reproducible paper as just one implementation that uses DataLad to do so. So if I click on this link, it takes me to a publicly accessible GitHub repository. Everyone can go there. You can go there. You can join me and do the same thing that I'm doing. And that's a manuscript that we have published earlier this year. And you can also read the PDF if you want to, but you can also just create the PDF for yourself. So I will just follow what is written in the README of this repository in order to just give you the idea of how it is for someone who has not written this paper themselves. So this repository is by no means like a picture-perfect example, but it's something that actually existed, and we wanted to just use this workshop to give you concrete insights on real-world things that we're doing. So the first thing that this README instructs me to do is to create a virtual environment that is a secluded Python environment that I can use as a sandbox to just install Python packages in so that they don't interfere with system-wide installations, for example. And I'm going to create a virtual environment, a Python environment, and then I can install the Python dependencies that this paper has. So note that I'm not making use of a software container here. It would be possible, but here we chose to just go for a documented README instead. So what I'm doing is I'm just downloading the software packages that are relevant in order to produce the results, so reproduce the results that are reported in the paper. Once this is done, I have the software environment that the authors of this paper tell me is necessary to recompute it. And now that this is almost done, the next instruction is to DataLad clone the repository here, and I'm going to do this. I'm just going to copy this from here. DataLad clone. Nice. Sorry, I forgot. That happens when I live code. So now I'm cloning this repository. I need to re-enter the previous virtual environment again here. So now I have the virtual environment that I've just created. Okay, and the last instruction that this README file has is to run make in the dataset. Before I do this, I just want to show you how this repository looks like just after I cloned it. So importantly, what I want you to note is that there's no PDF. Instead, what you can see here is the leftovers or the setup for what LaTeX, that's a typesetting program, needs in order to create a PDF. So there's a tex file which contains the manuscript sources, and there is a bib file which is LaTeX way of storing references, and a file that's called results.tex, which I will talk about later, and some style and class files that are relevant for LaTeX. If I take a look at the data repository directory, then you can see that there are some directories in there, but if I take a look at the directory hierarchy in there, you can see that those look like empty directories, and those actually are sub-data sets that are not yet retrieved, so I haven't DataLad get. I haven't run DataLad get on these files. And if I take a look at the image directory, then you can see that there are some images already included, but probably fewer images than would be expected in a scientific manuscript. So if I now run make, there's going to be plenty of stuff that happens, and I have a couple of minutes while this runs. It's luckily a very fast computation to just talk about what is happening and shed some insights on what is going on here. Now, the problem that I'm in principle facing here is that this paper that we have written has been growing for months, and we've extended the analysis that we have run, and so it's quite difficult, quite elaborate setup and quite difficult to explain when you take a look at the finished product. But I will make an attempt to do so, and I will later show you a much more distilled down and reduced template where you can try to do the same thing on your own, which is easier. Now, what is currently happening is that the algorithm that we wrote in this paper and what this paper is about is computing results. And you can see that whenever we have these progress bars here, there is DataLad in the background at work, downloading the required data to perform the computations that are necessary from the subdata sets that are linked in this repository. Something that makes the output of this reproducible paper very wordy is the print statements, or these weird new command definitions that are printed to the terminal. And I will shed some light later on how that works exactly. But what this leads to is the fact that these results that are numerical elements that are part of the result tables that are included in the paper are not hard-coded in the paper, but currently basically read from what is computed and then dynamically incorporated into the finished manuscript. So what you will later see as finished tables in the paper has never existed in that form in the original TeX manuscript. It has been included on the go during the computation that I'm currently running. And what is very nice about this setup is that I, as a consumer of this paper, only had to run the command make in order to get everything going. And this is what this guidance rule of the computational reproducibility guideline refers to. And this is one way of implementing it. And I will later show you the contents of the make file, which are actually not very complex or much shorter than you probably expect them to be, because the make file basically orchestrates everything in the correct order. It's not a DataLad run command, but it's an alternative way to schedule the appropriate time for the execution of the various functions of the manuscript building and so forth. And we're still downloading data and installing subdata sets. And you can see also that the algorithm that is executed here produces some output into the terminal. And we just have to wait for a couple of seconds longer, and I take a sip of my tea.
Adina, I have one question actually. So what I also noticed, what I also just saw in your output is that if you're cloning or like installing a subdata set, that sometimes you get this message that the submodule head gets detached. And I was wondering about that because I thought that within the .git modules file, the specific path or the specific commit of the subdata set is recorded. Mm-hmm. But then if the head is detached, like shouldn't it always be kind of up to date, or is it just letting you know that the input data set has evolved from that and you're actually at a previous commit for your current data set?
Could be both. It also happens if you have recorded a sub-project commit that isn't actually published, and then it will reset it, but transparently in a recorded fashion into the one state that is the most recent one in this installation. But it also happens like if there's if it has evolved further.
Right.
Okay, so now there was plenty of output, because what you have seen was Inkscape rendering figures, and then LaTeX doing its magic, which is also always a very wordy thing to happen if you compile LaTeX in the terminal. And if I open up the resulting PDF that has now freshly been created on my computer as a consumer of this dataset, then I have a scientific manuscript that looks just like any scientific manuscript. It has tables like these ones here, and it has figures like these ones here, and more tables, and more figures, and even more figures. And the important and very nice aspect of this manuscript is that all of these figures weren't existing, and none of the results reported in the table were existing when I cloned this repository from GitHub. Because if I take a look into the TeX file that I'm using here, and I'm really sorry for everyone who is not used to working with LaTeX, because seeing LaTeX when you're not used to it looks more complex than it actually is, unfortunately. But here are the contents of this TeX file, and if I go to, let's say, a line where I can show you a table, then you will see here's a table. But this table does not include any numeric results, so I never had to hand copy paste results from my interactive Python sessions or from any outputs. But the table that is created here references variables, LaTeX variables that have a name that I can identify. And the place where these variables come from is specified in this short input statement here. It reads them from a results dev TeX file. So even though this looks quite complex, the only thing that I wanted to demonstrate here is that there are no results that are hard-coded in the script, but they are embedded with a little bit of LaTeX knowledge from an external file. And the results that dev TeX file, this is a file that only includes the output that has been printed to my terminal while I was running make on that in this repository. So it's a verbatim copy of the standard output stream of everything that has been printed into my terminal during make. I will show you in the make file how this is executed. And I can show you the very simple thing that in the code script that is included here performs this thing, which are simple print statements that, for example, here, just compute whatever result it is I want to compute and print them in a new command expression. And the new command expression, if you're not used to LaTeX, is one way of defining a LaTeX variable, like the one that I've included in the tables. And now the only piece of magic that is left to decipher is what is in the make file. And the make file is really quite short. It says, if you have not been so if you're not used to seeing make files, it's fabulous and very robust and incredibly old construct, which you can basically think of as a recipe that tells you which things are dependencies of one another and executes them based on timestamps in the correct order. So what this makefile says is that the final result that this recipe should build is main PDF. And in order to build main PDF, it needs to execute the following command, which is a LaTeX make command, which is a LaTeX compiling tool that can do references and main manuscript generation quite nicely. And in order to execute this command, the following files need to be there, or the following steps need to be done first: main TeX references.bib results.tech figures. And in order to, for example, create this dependency, the make file needs to run the following command, which is done if the following file is there. And that command boils down to execute the script that makes figures and stats, and then pipe the outputs of this file, which do all of these print statements, with the Unix T command into the results dev.tech file. So it's really just a Unix hack of redirecting some streams into another file. And that file can then be integrated into the manuscript with this simple input statement. And in order to make the figures, there's some Inkscape rendering that transforms the SVGs to a PDF in order to look nicer. But that's basically already all of the magic that has happened in this makefile. It's execute this script, which has some print statements, and then save whatever it outputs into a separate file that you can include into the manuscript to embed your results on the fly. And that's one way of doing it. And it's arguably not the most easy one. It's just that I'm a weird person and like LaTeX and those Unix pipes and so forth. But what I also wanted to show you is some of the advantages that DataLad has been giving me throughout this, or us throughout this process, and how DataLad is used in this more complex project. So if I run the DataLad subdataset commands again, then you can see that at this level of the dataset, there are already some subdatasets available. So raw eye gaze and study forest data eye movement labels, that's input data, and RemodNav, that is the algorithm, the software that we're using and reporting in this paper. If I operate the same command recursively, then I can get an even larger list of datasets, because now also the subdatasets of our subdatasets are reported. And one thing that I wanted to talk about, just because I really enjoyed having this feature of DataLad at this point, is the following subdataset, where I will just quickly go into and demonstrate something. So this dataset is a dataset that we used for testing our algorithm on actual data. And we don't know the people that have made this data available. It's really kind of super cool. And we've made use of it. It's an incredibly useful dataset for us. So thank you to the people that have made that public. Thank you, Dr. Anderson. But the thing was that we had computed all of the results, like the manuscript was basically ready, and I was writing the discussion to this paper, and I found another paper that also used the same data set for a different purpose, and they reported that they found an error and fixed it in the input data set. There was a labeling mistake that they had to fix prior to computing their analysis. And just to be sure, I went into this dataset and checked whether this fix was contributed upstream. So whether the people that originally found the problem actually fixed it in the original dataset. So thankfully, a subdataset has its original history, so I can go take a look. And you can see that this dataset came into existence in 2018 and in 2016. And in 2018, Richard Anderson uploaded a folder that consists of the data files that they used in their publication. And I checked the file where the errors were reported, and I found out that the error was not indeed fixed. So what I did was I opened up an issue and said, okay, there's this paper, it reports an error and it has fixed it. Shall we fix the data upstream for you? And they said, yes, sure. So I submitted a pull request where I relabeled everything that was an error in the respective data file, and that commit was merged. Now, what this means is that the data that existed in 2019 and the data that existed in 2018, they are different. And different data means that results change. And that's a general and large threat to reproducibility if you don't make it transparent which data you're basing your computations on. And because I can link the subdata set in the 2019 version or in the 2018 version, I can make it quite clear which data I'm using. But beyond that, because I have used this LaTeX-based setup of a dynamically reproducible manuscript, I don't need it to recompute all of that, all of these results by hand, and I don't need it to hand copy paste and check every single file, but I just had to run one more make in this dataset to have everything updated in the dataset, in the manuscript again automatically. And at this point, the time that I spent, the extra time to not copy paste tables, but create those tables with these variables, that was well made up, because that was 1 minute, whereas I would have spent probably 2 days on recomputing something when the data has changed. So that's something that I can generally recommend a lot to do. And so as a quick disclaimer, that's not the only way to do it. I know that there are people in the audience, Aaron and I think Andreas, if he's still there, that have authored a really nice preprint on how to do this with Our Markdown, and Lennart will also showcase how he has done it with Our Markdown. I also want to say this is not the easiest way to do it. I never really want to I never want to claim that, but it's one way of doing it, and it's the one that fits my style, because it's the tools that I've been using anyway. And you can redo this with the tools that you're familiar with, and you can connect. You can use DataLad in a way, for example, to only connect the data to the results or to the repositories that contain your analysis. And in order to make the setup a little bit more transparent, we have created a template that is much simpler than this in this real-life example, where we have distilled everything down to the basic principles of how this works, where there's a cut-down script, which is only the classification analysis that I have already shown you in the basic session, that computes a very, so the analysis that you already know, and then includes the analysis results into a LaTeX file. And a make will produce the dynamically generated manuscript with freshly embedded results for you. And if you want to, you can take this template and explore it and adapt it to your use case if you are interested in redoing such a LaTeX-based reproducible manuscript with a kind of easier start than this very complex, already finished product. And there's a hands-on that we have planned with this, but I would probably place it at the end of the session to just gauge people's interest in whether they are interested in it. And Lennart can now show you how to do it in a not weird way that is making use of more modern tools that are easier to use.
Thank you, Adina. Can you quickly make me presenter again?
Yes, when I find you. Yeah. Should be good to go.
Okay, can you see the screen? Yeah, good. Cool. Thank you, Adina. I think that's your reproducible paper that you just presented. First of all, I think it's really awesome in general and in a very cool workflow. But also, I think your example of really nicely highlights how important it is that you can easily recompute results and fix errors in input data, which we basically talked about in the beginning, right? That data can change, there can be errors, there can be fixes, and you need to be able to tell which version of the data you work with. So yeah, like Adina introduced, I just wanted to highlight a slightly different approach, which might be interesting to a few people who also use R. So I actually like using R. I learned it during my master's and then kind of continued with it because I also like the plotting in R and so on. So I actually use it quite a bit. And And also R, as many as R users will probably know, R users R offers this feature of Our Markdown notebooks. So you can basically combine analysis code with text, so Markdown-based text, to kind of have a narrative around your code and your results and integrate it all in one notebook. And then you can render this to different types of outputs, for example, HTML or PDF. So theoretically, you could also write an entire paper or book or whatever in our Markdown and then render it into one long paper. And so I just present one output here that I did just actually for fun to try a few things out for actually my current project. So as Adina mentioned multiple times, I very recently acquired new fMRI data. And if someone is interested how acquiring data during the pandemic works, I can tell you more about it later. It's a lot of fun, a lot of disinfectant that you need to spray everywhere. Anyway, so what you can see here is a rendered R Markdown file, rendered as HTML. And actually, as you can see up here, it's actually a URL. So this is a website, not just an HTML file that I opened in my browser. And I will tell you in a second how I get this HTML file to this website. But first of all, so I'm just going to walk you through the basics of this HTML file and what it does. So it's a very simple script. The only thing it does, it is supposed to analyze some demographic data of the participants that I collected in my fMRI study. And so there are different ways how to do it. Here I just show in the beginning which R packages I use, and they are loaded up here. And then I actually get the participants' data and I load it into our Markdown. And so here you can see the path of this data, and the input data in this case actually comes from a bits data set. So I converted my MRI data to the brain imaging data structure, which is a community standard for organizing MRI data. And these bits data sets usually have what is called a participant's TSV file. And according to the bits documentation, like I wrote here or cited them here, the purpose of this participant's TSV file is to describe properties of participants such as age, sex, and handedness. So I created this participants file for my study in a bits dataset, and I loaded into our Markdown. And with our Markdown, there's a package called DT that you can use to render a nice table that you can look at, and you can go through all the rows of all the participants to look at the raw input data. So actually now I will switch to the view of the repository to see kind of the structure of the data set, and which is up here. So it's simply called zoo test because I tested a bunch of stuff, and zoo is my study name, and that's why there's a cute turtle up here. And you can see here that you find this R Markdown file that I mentioned. It's just here in the root of the project directory. And then you can see files that you now should know from belong to DataLad or that DataLad creates, like this Git modules file or the Git attributes file. And actually here you can see this bits folder that you saw before in the path. And this actually is a DataLad subdata set. So actually, I'm on GitLab now, so this is the GitLab instance of the MPIB. So actually, I could now click on this link, and it will bring me to my bits dataset, which is an entirely independent DataLad dataset with my bits converted data. So here you can see a typical structure of this bits dataset. Actually, I took the liberty to add a bunch of other files that you can ignore in bits, however. I hope Stefan is not mad at me for that. So this way you can see this is completely independent, and I just use it in my analysis kind of upstream and use it as an input data set. So basically, Yeah, and then I read this participants CSV file. But it's not directly part of this data set, but rather a sub-data set that I here include here. So back to the script. So what I then can do with our Markdown, I can do fun things similar to what Adina did in LaTeX. I can do things like that. For example, I can write a sentence that says participants were on average m equals 24.21 years old. And this sentence, I actually didn't write it directly into the text part of this Markdown file, but instead I used R code to actually calculate the mean data of the participants and round it to the second decimal place, and then included this code chunk into the sentence. And it actually makes more sense when we look at maybe the raw data files, so the source code, which you can see here. Exactly. So this is how it's included in our Markdown, and that way, when we render this R Markdown file, it shows up like this. And that's a very nice way how we can just generally integrate actual computations on actual data with the narrative around the data. And then we can do other stuff, like, for example, I can create a nice pie chart, which I don't recommend to do in an actual publication because I was told that no serious researchers uses pie charts. But still, in this case, I can do it to just show how many female and male participants on my data set. And finally, I can list the computational environment. So there's in a very simple way, I can just list the R version and packages that were used. There's a special command in R for that called session info. And then it lists all here. Up here is the R version, and down here are some of the packages that were used. That's just a very similar workflow that Adina presented, just using different tools. And of course, this can be extended. You can use multiple Markdown files and combine them and actually integrate more data. Maybe the last kind of interesting bit that is remaining, that was actually the purpose why I created this simplified repo, was how I could get this website. And we mentioned one aspect earlier, that is continuous integration, which I'm not for the first one, I'm not an expert on this, so maybe someone else, or Adina, you want to chime in to explain this in more detail. But basically, continuous integration means that, or software developers use it a lot to basically, when you push changes to a repository, that then a certain script is executed and runs some computations on the data, or for example, some tests. We mentioned unit tests today, so you could actually run some tests on the data to see if something has changed about the input data. And then and you can do this automatically without you needing to execute these scripts. And the interesting part, which is possible both with GitLab but also with GitHub, is that you can also host web pages on GitLab and GitHub. So basically, when I create this R Markdown file, this creates an HTML file, and because an HTML file I can easily use as a website. And I do this through continuous integration. And disclaimer, I think that's not the most ideal way to set things up. But in this very basic version, what I basically did, and I will briefly walk you through it. So this shows you the file that kind of configures this continuous integration. And Adina mentioned containers before. So here I'm actually using a very old DataLad container. So I think the most recent version is 0.13 something, right? And so here I use a very old version of DataLad, 0.11.7, that Chris Markiewicz created at some point. So I didn't even create this container. I just use it for my purposes, right? So even if you have no clue or don't understand how to create containers yourself, you can still use them and use containers that others created. So then I do a bunch of other things. And actually, so what I do here, I install a tool called rclone. And this is a kind of a primer for our later session when we talk about configuring rclone remotes, which is another way to publish data to different types of data storage systems. And here I'm going to use rclone to get the bits data set from this C file remote repository where the data is stored. And as you can see here, in this continuous integration, the script basically gets the original bits data set or kind of clones the original bits data set, enables the storage system that I'm using in this file, in this case keeper, and then it gets this participant TSV file. And it then basically provides this file as a so-called build artifact. So it provides this folder with the bits data to the next stage. And at this next stage, I'm using yet another container, in this case, a container for R, which is called Rocker, which has all the packages I need for my R Markdown script. And then I simply execute an R script command, and in this case, R Markdown render, that renders this demographics R Markdown file that I showed you before to an HTML document. And the final bit is that to actually publish this R Markdown document as a website, I need to put this HTML file into a folder called public and rename it to index.html. So that's what you can see here. So I create a new repository, directory public, and I move the demographics HTML that was created by the command before, and I move it and rename it so I move it to public and rename it to index.html. And the end product again is this public folder. And from this, GitLab is able to create this website, or this then ends up as the rendered website that we're looking at now. I think that was a bit kind of a tour de force through like all these steps, and it incorporated a lot of different things. This setup of rclone and how I get the data, we will present this in a dedicated workflow later during the final session. But this is just to highlight how you can use, for example, continuous integration to also automatically get data from sub-data sets and then run automatic computations on this data set. And this website, in this case, I have to admit it's not public, but you can make this public and make it then available to others. But also you can keep it private if you want to be more secretive about your project, but then you can still add, for example, your supervisor. And then when you have a meeting with your supervisor, you could just send them the link to this rendered HTML document. And this way you have a very nice way to look at recent results that you created. Are there any questions about that? I have the feeling it was a bit rushed and a lot of weird details that are maybe hard to grasp at the beginning. But this is just as an illustration of what you can do and where you can bring lots of different tools together. So in this case, R Markdown, continuous integration, and DataLad, obviously. I see there, let me just check another question. Okay, Stefan asked about how I get different outputs from other tools into R Markdown. Exactly, like Aaron said, like you can also use other languages in R Markdown. I think similar to Jupyter Notebooks, you can combine actually across multiple languages. I haven't tried that so far, but what I kind of do here, which is a, simplified version, if you just want to show the contents of some other script, like a Python script or a Bash script, you can also do it in that way. So for example, here I just include this GitLab CI file, which is a YAML file, and then it should just be displayed as part of this R Markdown file, but it's actually not executed. So I think if you want to execute both R Markdown code or R code and Python code within the same continuous integration, then you would need to set specific chunks within this R Markdown file that then also can execute Python code. It's possible, but I personally haven't tried it before. Yeah, and Aaron is also posting a different link of a different package called Bookdown, which I think its main strength is to combine across multiple R Markdown files. So you can create another R Markdown file where you analyze the behavior data, and then you analyze some other data, maybe that comes out of your MRI pipeline, and then you can combine them to, in the end, one paper if you want to. Any more questions about the R Markdown pipeline?
Someone is typing, so let's wait for that.
Can you share the code? Yes, sure. I will do that. Maybe not now, because then I'm too distracted, but later. Sure.
Cool.
There's also an improved version. Like I said, this GitLab, especially the continuous integration part, it's not ideal. As you can see, it uses a quite old version of DataLad, and also this Rocker image, especially this Docker image verse, actually includes a lot of R stuff. I think it even contains a full RStudio installation. So when you run this, I mean, this code is executed, and this can take quite a while. So I spoke to our sysadmin, Michael Krause, and he already recommended several ways to me how I could improve this continuous integration, and actually maybe start to write my own Docker files that are reduced to only the stuff I need. But as I mentioned before, I think if you get started with Docker or containers in general, it's sometimes helped just to use containers that other people have built, and then maybe look at how they build it, and then you start making your own changes to it.
Thank you so much. I think R Markdown is an incredibly powerful alternative or tool in general. And even if we have lost some people in the audience with this overview of workflows that we in our own day-to-day science use, the one take-home message that we definitely want to try to get to people is not how in particular these things work, although we're happy to share the code, of course, and the template with the Python and LaTeX setup should definitely get you started, and it's well commented and documented. But what we are trying to show you is that even though we have a lot of different tools between the two of us that we're using and that we know about and that we find valuable, we just connect them in an interoperable fashion in order to create something new. And I think that's something that is often lacking in tutorials or in informal teaching sessions, this knowledge of, hey, I can actually be creative here, and I can take the tools that I use and just stick them together or puzzle them together into something new. And in my opinion, once I started to think in this interoperable or in this piecewise way, where I can just pick whatever I want, whatever I already use, whatever I find, whatever I'm comfortable in using or interested in, and then figure out how I can integrate it into a workflow that suits me well, I got it's getting really fun, and it's definitely a nice feeling once you have all of this software stack that you have connected, and then it works, and it's getting easier and easier to work to get to work. And now that I've seen how our Markdown works, I'm actually quite envious. That's a really cool setup that I should look more into. Especially since I now learned from Aaron that I can also include other programming languages into it.
Yeah. Maybe just because Aaron mentioned it, this package, R package Bookdown. So just to show you, so I actually also used that before. So, no, that's a different one. There we go. So that's a very basic overview of what Bookdown looks like. So basically here I'm trying what I mentioned before, trying to combine across multiple Markdown files and then eventually combining them into something that is maybe closer to a paper or some sort of report. And you can see on the left, you can have these different sections, and you could write an introduction. And actually, this is not complete yet. I just dropped some citations there, so you can also include BIP files, so BIP LaTeX files that contain your references, and you can include them in Our Markdown and basically cite them. So if you were skimming through my notes in this introduction, it's really just notes, right? This is super early work, so bear with me. It's not close to anything complete. Like I said, I just acquired the data. As you can see, I'm interested in kind of cognitive maps and replay and stuff. Actually, here you can see this participants file again, actually with the same pie chart that I showed you before. And I think I added a bit more stuff and information about the participants and how the study was conducted and about the task and so on. And another thing that I started here in the supplementary, that's what I mentioned before. So this goes into the direction also what Stefan asked about including different code. So here I'm just showing, so this is just kind of passively showing other code that I use, for example, to convert my data to bits, which I do on our high performance cluster. I use a bash script, so this is just showing you the bash script, for example, that I use to convert my data to bits. But this is also really just meant as a documentation, basically, so that in this rendered version, someone who's interested and doesn't want to, just want to get an overview of the script that I used, could go to the supplementary, basically, and look at the individual scripts that, for example, converted my data to bits or defaced the data or stuff like that. But it's not as cool as what Stefan is after, to really compute with different programming languages in one notebook document. This would be another great idea. Thanks for sharing.
I'm going to steal the presenter back from you. I realized that we are running really late, so and I've also already spotted some very good questions in the shared document. So what I will do now is okay, quick summary. So I hope that it became clear how a reproducible paper is very useful, but also that there are many tools that allow you to create a reproducible paper. And there are probably even more than the two ways of doing it that Lennart and I have just shown you. And it's a way of creating research that may interest you, and then you can pursue it. And we hope that we gave you the inspiration, if you have never done something like that, to try it out maybe in your next project, or just as a nice distraction from work if you're up to it. The setup has a number of advantages that are definitely contributing to a more reproducible scientific procedure. So for one, it saves you time. That's something that's not only a benefit for reproducibility, but it's a benefit for you. It saves you time, even though you need to think into the setup, of course. But in the end, in my personal experience, it was a lifesaver and a time saver. You also have this framework of collaboration, and I will just quickly show you here the repository history, the dataset history that we have accumulated throughout the lifetime of this project, where the three authors that have worked together on this project, and we were spread over multiple continents while we were writing this paper, have been able to collaborate in real time because this was a repository on GitHub that we can easily access and then just push our updates to. One thing that certainly helps with the general well-being of a scientist, in my opinion, is that a paper like this helps you to gain confidence in the validity of your results, because you cannot mistype, you cannot miscopy, there cannot be a switch decimal place. Your code is public and you have your co-authors and the general public and the reviewers look over it, and it's much more likely that people can find and fix mistakes, which contributes to the overall progress of science. So making a mistake is completely human, and that always happens, and so many mistakes that I did in this paper were found by others, and I was incredibly grateful that the published document has had all of these people look over it and eradicate all of the mistakes that they found. It also makes a more convincing case with research if you are able to do something like this, because it allows others to verify what you've done, to check the code, to also adjust the code, and you can make your research accessible and, importantly, adaptable for everyone. So if someone comes around and says, hey, the algorithm that you wrote, that's a nice toy, but I can do that better, definitely, then this person can just take the algorithm, play with the code, rerun the same analysis on the same data, for example, check whether the results are better or not, and just tweak it. And that, in my opinion, accelerates the pace in which we can make progress. So in my opinion, that's something that is worthwhile to pursue, and it's also definitely fun. So that paper, I'm really proud of that paper. It's making me physically happy. I got so much serotonin out of that. I can recommend it. Okay, and now I will just quickly run through the software environment section, where I just share a couple of code snippets and tool recommendations for sharing software environments with the DataLad containers extension, just so that we can get to the publishing section as well. So there are two main reasons, I think, why it's very useful to share software containers. One, it is difficult and sometimes even impossible to install software, especially if you're in a field that uses, let's say, quite complex software. For example, in neuroimaging, where we have tools like AFNI or FSL and stuff like that, that can be a pain to install. Also on, let's say, high-performance compute clusters, where you don't have administrative rights to install those tools, or if the tools that you need in the precise versions that you need them conflict with system-wide installations. So sharing a software environment helps the person that executes the code to not have to go through 2 days of hell to install whatever is necessary to perform an analysis. And that person can very well be yourself too. Another reason why sharing software environments is really important as provenance is that different software versions or different software that has been compiled with different compilers on different operating systems with different versions of compilers can produce different results. So here's an example of a study from 2015 by Tristan Glattard. And what they just found is that they compared common software that neuroscientists, neuroimages use that has been compiled on different operating systems and executed on different operating systems. And what they found, for example, is that different versions of the same compiler resulted in different floating point precisions. And so what you can see here, hopefully a little bit with these red highlighted floating point values in this result, that two different versions of the same compiler produced a difference in results. And that's dangerous, because you don't want to have, when you're really focused on computational reproducibility, then you don't want to have the extra uncertainty that is added by different floating point precision or slight differences in floating points, because they can, depending on what you're researching, really have a huge impact. So if you can encapsulate a software environment that can be kept the same across people that run it, then that can prevent such things. So software containers, if for those that have never heard of software containers, they encapsulate a software environment and isolate it from the host operating system that it runs on. And there are two common solutions, Docker and Singularity, that I'm quickly talking about, but there are many more. But I also don't know much about those other solutions, so I'm sticking to those two solutions that I'm aware of and that DataLad can work with. I wanted to quickly ask you how familiar you are with software containers, just to get an idea of what you know already. So have you ever heard about software containers in general? Cool. That's something nice. Have you ever used a software container? Perfect. That's very nice. And then, have you ever created a software container yourself? Cool. So for the people that said no, it's absolutely no requirement to ever produce a software container yourself, because there, for most standard solutions, are already pre-made containers that you can just use. But I hope that I can shed some light on how I use some tools that help me to create software containers, where it's actually much easier than one would think it is. So just as a quick introduction, and I'm very happy that this is a virtual course, so no computer scientist can throw rotten tomatoes at me. I'm trying to explain software containers, but I'm a clinical psychologist, so you know how well that will work. So a software container is, if I overly simplify it, a cut-down virtual machine, and it is a portable and shareable bundle of software libraries and their dependencies. And it includes a couple of things, namely code, runtime, system tools, system libraries, and settings of the software that you want your software environment to have. But it does not include certain things like the resource management that the host operating system, so whatever computer you're using, whatever that computer runs, provides. So I took this graphic from the Docker website, where you have a Docker container or a Singularity container. That's what this little icon here is, that basically sits on top of the host operating system and gets the resource management from there. But the container includes everything else that it needs to have an encapsulated, isolated software environment that you can ship to others, and where you can have multiple different applications basically in software containers on the same system running, which is a useful thing to do. And just for a quick glossary, because I myself often had problems to distinguishing those terms when I started to learn about containers, there are four vocabularies that I want to distinguish, or that I just want to quickly explain. When we talk about a container recipe, then what we mean is a text file template that basically just lists all of the required components of the software environment that we want to create. And in the case of Docker, that's a Docker file. And in the case of Singularity, that's a definition file. And those files typically end with a .dev extension. Now, from this recipe, you can build an image. And the image is just a static file system that is populated with the software that is specified in the recipe. It basically describes all of the software that you wanted to run in the software environment. And when we call something a container, then that is actually a running instance of an image, so of this static file system, which is actually in use. And so when you build a container, or when you use a container and make it from scratch, you start by writing a recipe file, build it into an image, and then run that image in order to have a container instance that you can use with the software that you specified in the recipe. And then there's also the concept of a hub, which is a storage resource that you can use to share your own images, or where you can consume images from. And Docker and Singularity Hub, they each have their own hub, Docker Hub versus Singularity Hub, and they are really, really useful resources. So what's the reason for those two solutions? Docker has existed a little bit longer than Singularity, and Docker is a widely popular container solution. But Docker has a really large disadvantage. It requires admin privileges in order to run. When you execute a when you use a Docker container in a system that you have full admin privileges on, then that's no problem at all. But the problem arises when you are on shared computational clusters, because if you execute if you are in a container, in a Docker container, you will be root, so you will be admin, you will have sudo rights. And on shared computational infrastructure, this is disastrous because this can do a lot of harm to shared infrastructure, shared data, other people's data, and so forth. And no sane sys administrator will ever let you install Docker on their system. So Singularity was created as the scientific alternative to Docker, so to say. And Singularity is built to run on computational clusters. The way that the main difference is that when I use a container, I am the same user outside as inside of the container. So I don't have elevated privileges, which makes Singularity a safe and employable solution on computational clusters. It's also a little bit easier to access GPUs with Singularity containers and run graphical applications, but the main advantage is that this type of container solution is portable to HPC infrastructure. Singularity, however, is very, very user-friendly towards Docker images. So if you're using Singularity, then Singularity can actually use a Docker image, pull a Docker image or build a Docker image and run it natively, which is a very nice thing. So if you have something, if you have a Docker recipe or image, then you can use Singularity to run it, which is nice. And DataLad can register both Docker and Singularity images to datasets. And it does so with the DataLad containers extension. So I've shown you already how I have used it, but just to add a little bit more details to that, so a DataLad extension in general is a Python package, a standalone thing that basically powers DataLad up. It's just an additional range of commands that once you have installed the extension, get added to the DataLad command suite. If you install DataLad containers, you get 4 additional commands: DataLad containers add, DataLad containers list, DataLad containers run, and I forgot the 4th one. But in this way, extensions work. And there's also other examples, for example, DataLad OSF, which lets you publish datasets and clone datasets from the Open Science Framework and so forth. Or DataLad Hurny, which is useful for converting DICOM datasets into bit-structured datasets. Here's how to install DataLad container. It's a pip installable, so you can just go with pip install DataLad container. If you're on a Mac, it's probably pip 3 if it's a recent operating system. The way that DataLad does this is really simple, because a software container, even if it's the layers of a Docker image, is just another file in your dataset, basically. So DataLad conceptualizes that the software environment is nothing particular spectacular for DataLad. It just sees it as another type of file that it just saves into the dataset and can register it from its URL or from the paths that you have installed it from. And because in the basics I only have shown you one way of installing or adding a software environment to your dataset, I just had encoded concrete code examples on how to do this here in slides. So first of all, I'm going to show you how to do it with Singularity images. The first question maybe, first I'm showing you how to add Singularity images from a path. So in the basic section, I added a Singularity image from Singularity Hub with a URL, but you can also do it from a path. The first question may be, how can you get Singularity images? And one way to do it is you can pull it either from Docker or from Singularity Hub. You can see 2 examples of how this is done, where I'm just pulling different images that are hosted, and Singularity works with both of these hubs. You can also take or write a recipe file and then build a container, an image on your computer. One thing that's inconvenient here is that you need to do it with sudo, so elevated privileges, and I'm going to show you a workaround how you can circumvent this. And once you have a Singularity image pulled or built on your local system, these things just lie around as one single file, and they typically have a .zip or .zin extension depending on the version of Singularity that you're running. And then you can point DataLad containers at simply to the path on your file system where that container lies, and DataLad will register that container to your dataset and is able to use it afterwards. And if you then do a DataLad containers list, then it will show you all of the computational environments that are registered and available for use. Note that you can give unique names to your containers, and that's later. That's important because you want to precisely identify which container you are using in a DataLad containers run command. So the name of the container is a required argument. And what's nice about Singularity images is that they are a single file. And you will see with Docker, it looks a little bit more chaotic when you use them. But I would advise against using path to add a Singularity image, because that is not as portable if the registered location is on your local file system. So instead, I would always advise to register images from a public URL, because then you can, on other infrastructure, or others can, on their infrastructure, retrieve the image very easily. So here is another example of adding a Singularity image from Singularity Hub from a URL, and this is a publicly accessible URL that others can simply DataLad get the container from. If they need it, and where a DataLad rerun of a DataLad containers run record will retrieve the container automatically from. And my workflow personally, to just share with you how I do it when I create my own images, because it's actually, so it's not that complex, and many people make it sound quite complex, but it's something that with a couple of helper tools actually works nicely, and you have a steep learning curve, but you can get to building your own Singularity images fairly soon. So I have a really basic workflow. I'm almost ashamed because it's so easy, and I'm using so many tools to help me, but it works for me, so maybe it's helpful if I share this. So what I do is I create a data set, and then I use a tool that is called NeuroDocker that helps me to create a recipe file. And it's really, really simple. And NeuroDocker is one of the tools that Repronim is maintaining. And it's made for easy installations or for easy creation of Docker Singularity images of neuroimaging software. And I use a DataLad run command to create a Singularity recipe via NeuroDocker, and then I link the repository that I host on GitHub to Singularity Hub, where I can log in with my GitHub account. It's a free service. And Singularity Hub then ingests the recipe, if I enable that, and builds the image on their web service, which is very nice because I don't need to use sudo to build the image. And then I get a public URL from which anyone can register this image from. So here's a quick demo. Here is one of the repositories that I use whenever I need to write a Singularity image for the DataLad handbook. It's a really small, really small repository. It only has this directory envs, and in this directory envs, I have a shell script that's called generate sim.sh. And I'm really cheating here, but here is what this script executes. It's just a Docker run command of a public Docker image of the NeuroDocker container. And NeuroDocker makes it really easy to create Singularity or Docker recipes. I tell NeuroDocker to generate a Singularity image. I want to base it on a certain operating system. I want to have a certain package manager, and here I can now, for example, specify the precise software that I need to have installed. And this is a very minimal example. It's a tiny file, but NeuroDocker has ready-to-use commands and examples to really, for example, if you have the need for very complex software libraries, where you can just add them as one argument to your invocation of NeuroDocker, and that writes the Singularity recipe into a file. I am lazy and have a bad short-term memory, so whenever I change this script, I do it a DataLad run of initial DataLad run command that created the first Singularity recipe for me. And then I don't need to write a single line of this recipe myself, which is a nice feature to have. And I can then go to, Singularity Hub. Singularity Hub. It's a free service, and I can log in with GitHub, and I then have my collections, which are all of the repositories where I have enabled Singularity Hub to build container images for me. And then I get this collection where my Singularity images are being built. You can see that the status is complete. Whenever I push an update to GitHub, the container will be rebuilt. And this is a URL from which I can then pull the Singularity image. So that's something that has been working really well for me whenever I need a specific or slimmed down Singularity image that I can't get from anywhere else. Okay, a Docker image from a path adding is not a good idea. I actually wanted to get this out of the, yeah, I will just skip this. But here's how to add a Docker image from a URL. It's just the very same command. And I've executed this command on a system that doesn't have Singularity installed, but only Docker, which is a Windows computer. Windows, you can only install Singularity if you do it in the Windows subsystem for Linux. And for testing, I tried a Windows machine. And what you can see here is that it registers the Docker image from the URL, but it looks a little bit more messy because Docker images are actually not a single file, but every set of instructions, every software that is added to the Docker image creates what is called a layer. And that is this character string here that gets added as one snapshot by DataLad. But it's still a workable container image that you can use. It's just that it looks a little bit frightening when you take a look at some of the result rendering that DataLad provides. Okay, and then the last thing I wanted to draw your attention to is how DataLad executes things inside of containers. So if you're using containers, then you know that it's actually dependent on how you invoke a container, what this container does. And sometimes you have containerized pipelines that need specific arguments or a certain type of bind mount, so a linkage to certain directories that should be available inside of the container. So I just wanted to be transparent on how DataLad does the actual execution of stuff inside of the container, which is handled more or less automatically, but here's how you can configure it. So if you take a look into the .datalad config file inside of a dataset that has a configured container image, then you will find not only the URL where it's registered from and where it can be updated from and the path to the image in the dataset, but you can also find this command execution line, which is the definition of how this particular Singularity or Docker image will be executed. And in this case here, or the default case if Singularity is available on your system, is a Singularity exec with a specification of the image. That's a placeholder that will be expanded with this thing, and then the command that you give to DataLad run or DataLad containers run. But there are use cases where you want to configure that. And one way of doing it is to just open that file and write in whatever configuration you need. And another thing to do is to just specify the configuration right at the time of container adding. And that you can do with the call format flag, where you can basically exchange this string with whatever other string you want. So here's an example of how I invoke fMRI prep. And fMRI prep wants some specific arguments. For example, it's recommended to do a clean env flag when I invoke fMRI prep. And I also want to have certain bind mounts, in this case my working directory, and a license file that needs to be handed to fMRI prep, and this is how I can configure this. And if you're interested in finding out a little bit more, there's a link to a YouTube video where I execute a complete fMRI prep containerized pipeline workflow with the DataLad dataset and publish it to Jin for further info. And then I wanted to highlight a couple of useful resources, because it's sometimes not, or in most cases, not necessary to write a container recipe yourself or build a container image yourself. So a couple of helpful resources to working with software containers. One is Repo2Docker, which is a really cool tool, and you can point it to a repository or a dataset, and it builds you a container image from the configuration files that you placed in that, which is fantastic. Then, of course, there's NeuroDocker, which I use, that can generate custom Docker files and Singularity recipes for neuroimaging. So it has AFNI, FSL, all of these tools that it can do. Then there is a container collection, the Reproducible container collection, which is a DataLad dataset. And that includes a couple dozen containers with common neuroimaging software that you can just install as a sub-dataset. So you can clone this dataset as a sub-dataset, have all of these containers included in your data analysis, and use those containers readily available. And then there's Rocker, which is Docker for R users. Thanks for adding that, Lennart. And that seems to be a really valuable resource for everything R related. Okay, so for a quick summary, when we think back to all of these definitions, then I hope that we will be able to make a point that DataLad can assist in all of those things. For reproducibility, DataLad can provide automatic recomputation and identity checks of results. But with a DataLad dataset, it is also quite easy to do replication by just exchanging the input data and rerunning stuff, especially if you use standards such as bits and generic scripts that make use not of hard-coded paths, but for example, globbing for file patterns. You can exchange input data into your analysis and replicate them very nicely. Robustness is eased because DataLad makes it easy with a modular structure to reuse data and to change the code and then update the paper, for example, in this reproducible paper setup. And generalization is made easy if you share your analysis dataset in an easily reusable and adaptable framework, such as a DataLad dataset. You can assist others that try to build up on your work and try to extend it. Okay, now I think I have, I have spent too much time on this section. I'm really sorry. So there were a couple of hands-on sections planned with in this session, and all of them are on the workshop homepage. One hands-on was this reproducible paper template, and everything is documented. So if you want to take a look and just figure everything out, then you can do this still and just write as an issue if something doesn't work. And the second hands-on is running a containerized neuroimaging workflow, which makes use of the Reproducible container dataset. And everything that you would need to run is also highlighted here as copy-paste snippets that you can put into your terminal in order to do so. I have also included a couple of further reading links with more information if you're curious about software containers. And I hope that we can, instead of going through these hands-ons, go to the publication session, do a quick break with the toilet visit, and then get to the questions that people are having to discuss those.